Bhavana, please start. No more
Yeah,
interruptions.
yes, sir. So today we will be talking about fuel cells and fuel cell based electric vehicles. So the content of our slide is as such. So we will be talking about fuel cell introduction, what is the working of fuel cells and its characteristics, and the various fuel cells that we are using, we are using in our day-to-day lives, like proton exchange membrane, alkaline fuel cells, then direct methanol fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, solid oxide fuel cell, and hydrogen storage systems, reformers, and fuel cells that are used in electric vehicles, we will be touching upon. So basically, fuel cell. What is a fuel cell? A fuel cell is an electrochemical device that is producing the electricity by means of chemical reaction. So how is it different from battery if we think of such? So in battery, the chemical reaction takes place as long as the chemicals are taking part in the reaction. But in fuel cells, as long as the fuel is supplied, the fuel here we are talking about is hydrogen and oxygen. So as long as hydrogen and oxygen is supplied to the fuel cell, up to that time, it produces electricity. So the working of fuel cells, if we see at it, so the basic structure is similar to that of battery. That is, it is consisting of both cathode, anode, electrolyte, as such. The reaction, we are supplying, as I told you, that like oxygen and hydrogen we are supplying. So hydrogen, the reaction that is taking place at cathode, that is like we normally represent it as in negative sign. So in the figure we have it towards the left side. So we supply hydrogen to it. Like hydrogen basically consists of one proton and one electron. So hydrogen molecule, when we are supplying a hydrogen molecule, we have two hydrogen atoms there, and they are sharing their electrons with each other. That is, there is a covalent bond between them. And so when we supply to the anode, when we supply to the anode, there is the fuel cell reaction takes place as such that there is breaking of hydrogen. Breaking of hydrogen in the sense, we totally get four kind of constituent materials there. That is two hydrogen ions, that is essentially protons, two protons, as well as the shared electron. Two electrons are they are generated at the anode. And the flow of electron between anode to cathode will result into the generation of electricity. And the constituents like hydrogen and electrons flow from anode to cathode through the electrolyte that we have supplied. So this is different from that of electrolysis of water. Hydrogen and oxygen is combining to produce electricity as well as water. So there is no pollutants, or it is too environmental friendly. So the reactions are like shown, there is at anode breaking up of hydrogen into two H plus and two electrons, and cathode, the reaction at cathode are defined as such that as soon as these hydrogen and electrons flow onto the cathode, we supply oxygen. So this oxygen breaks the first reaction. There are two types of reaction that are taking place at the cathode. That is, oxygen is broken up, their bonds, that is O2, are broken up into their constituents oxygen, and they acquire the electrons and they become negatively charged. As they are negatively charged, these hydrogen, that is essentially protons, they combine with the oxygen to form water. So the overall cell reaction is such that H2 plus half O2 will give you water. Next slide. Yeah. So the characteristics of fuel cell is that this fuel cell operates isothermally. Isothermally, that is, temperature is maintained at the same constant, and also the free energy, that is we called as Gibbs energy, is directly
Correct.
converted into electrical. Yes, sir.
Correct. Continue.
Yes. So the free energy is directly converted into electric energy. So there is no loss, the loss that we see in conventional fuel system, that is cannot cannot cycle efficiency, like what we see, that problem is not seen here, because the free energy is directly converted into electric energy, and that free energy is used, like it is called maximum electric energy for fuel cell here, and it is defined by the equation that is, we normally give the Gibbs free energy as delta G, that is change in Gibbs energy is given as NF minus NFE. So it is minus because it is an exothermic reaction that is taking place here, and N is the number of electrons that are produced, and F is the Faraday's constant, and whose value is 96,412 coulomb per mole, and E is the electrode potential that we are using. So when we take this particular reaction, that is H2 plus half O2 gives you water, that reaction, if we take it at standard condition in the sense that is pressure is 1 atmosphere, and temperature is 25 degrees Celsius or 298 Kelvin. If we take it as such, then we have that a maximum electric energy as minus 236 kilojoule per mole. So the maximum reversible potential, the potential can be founded by Nernst equation. So the E is equal to E is the, we are finding the potential, and E naught is the potential at standard condition, that is 1 atmosphere and 298 Kelvin, and plus RT by NF, ln of partial pressure of hydrogen, partial pressure of oxygen, that is multiplication, and divided by partial pressure of water. So R is universal gas constant, whose value is 8.314 kilojoule per joule per Kelvin per mole, and N is the number of electrons that is involved, and F is the Faraday's constant, and T is the temperature that we have taken. And here we have used E is equal to E naught plus. So because we have taken the reactants on the top and the product on the bottom. So if we reverse this, it becomes E is equal to E naught minus of RT by NF ln of partial pressure of H2O divided by partial pressure of hydrogen into partial pressure of oxygen. Next slide. So we plot the graph of voltage current. We find that theoretically we get 1 volt, but practically this doesn't happen because there are a lot of ohmic losses that are happening because the type of material electrodes we are using, and the electrolyte, there is loss of there is loss of current there. So practically it is not possible to achieve 1 volt, and that is shown in the graph, that practically it is somewhere about 0.8 0.7 to 0.5, it comes out like that. And so the major advantage of this is also that it is sensitivity to scaling, that is even if you take it at kilovolt or megavolt, whatever you take it, the efficiency remains the same. The efficiency is not depending upon the scaling factor. What we mean to say is that. So next slide. So now we talk about the different type of fuel cells that we are using. We have majorly 6 type of fuel cells. So if we see at alkaline fuel cells, we use the electrolyte as aqueous potassium hydroxide because it is an alkaline and a spacer. So we have different types of fuel cells based on their efficiency and strengths and weaknesses, and for various other purposes we can use according to our needs. So first we have alkaline fuel cells. So in alkaline fuel cells, we are using the electrolyte as potassium hydroxide. So the advantage of this is that before we were using acidic electrolytes. So there was a problem of corrosion that was happening with the electrodes. So as we're using electrolyte as a alkaline electrolyte, so that problem is not there here, and its performance is also good. Its performance is good, and it has an efficiency of 60%. And the thing is temperature required here is low, that is 80 degrees Celsius. And cogeneration is not possible because cell temperature is not sufficiently high. So cogeneration refers to the extra amount of waste heat energy that is released by the fuel cell that can be used to generate electricity. So that provision is not there here in alkaline fuel cell because cell temperature is not for that cogeneration to happen. We need some particular temperature which is not possible in alkaline fuel cells. Next, we have proton exchange membrane fuel cell. It is called proton exchange membrane fuel cell because we are using like solid polymer as an electrolyte. Normally, we used to have liquid electrolytes, but here the thing is we are using solid electrolyte, and example for that is naphthalene. And it is rugged and simple to construct. So it is, but the efficiency is not that high as that of alkaline fuel cell. It is low, that is about 40%, and the temperature is also similar to that of alkaline fuel cell of 80 degrees Celsius. But the major advantage here is for alkaline fuel cell we had that again, sir, it is left.
Yeah. Sorry that.
Yeah, so the major thing in alkaline fuel cell, we were like we have had to supply pure hydrogen. There were like contamination of hydrogen. If at all that happened, then efficiency would not have been there. But here in proton exchange membrane, impurity tolerance for hydrogen is acceptable here, and but the efficiency is not that as that of alkaline fuel cell. And next we have the direct methanol fuel cell. So like the background of this is that there was as hydrogen is highly inflammable, so like there was like carrying it was a major disadvantage. So there was like search for a kind of where we could directly convert the hydrogen of that particular methanol into so that we could be it could be used for electric vehicles. So that was the main intention for direct methanol fuel cell. So this working principle is same as that of proton exchange membrane itself, but the operating temperature here is like quite high, that is 90 to 120 degrees Celsius, and efficiency is not that high. It is very low, that is about 30%. It is still in design stages, and it requires a lot of a lot of research to be done for its implementation. So the next type of fuel cells will be taken up by Kaushik.
Yeah. So thank you, Bhavana. So the next fuel cell we have is the phosphoric acid fuel cell. It is one of the oldest fuel cell. You can say like the fuel cell origin was first done by PFC type fuel cell. So as the name suggests, that the electrolyte used is phosphoric acid, and then we have the operating temperature of about 200 degrees Celsius, and electrical efficiency is 40%, which is quite low. And the cogeneration here is possible. Why? Because we can see that temperature is around 200 degrees Celsius. So generation of heat to like you can say a satisfactory level is possible. So we can say that cogeneration is also possible. But there are some drawbacks of using this fuel cell. That is, it's not suitable for a vehicle application. Why? Because it is too bulky. Whereas on the other hand, it can be used for stationary applications because of its higher efficiency. And there are many designs based on PAFC, which is suitable for stationary applications. So that's why PAFC is more preferred for stationary applications compared to vehicular applications. Next comes the molten carbonate fuel cell, abbreviated as MCFC. So this originated from the development of like to operate directly on coal. There was a need where coal was supposed to be used for giving power. So once that research started, it originated to a fuel cell type known as MCFC type fuel cell. And here the electrolyte used is carbonate. At operating temperature, as you can see, is 600 degrees Celsius, which is quite high. And this higher operating temperature also makes it one of the reason not being used for vehicular application. And the
Correct.
requirement is that it has CO or CO2 on the cathode side and hydrogen on the anode side. electrical efficiency is about 50% and cogeneration is possible, obviously, because the temperature is quite high, so cogeneration is also possible. And like I said, it is not used for vehicular applications, but it is good for stationary power generation. Next comes solid
Can
oxide.
you explain what is meant by, can you, Kaushik, can you explain what is meant by cogeneration?
Cogeneration, as the name suggests, that it is co-generation. Like there is a generation of electricity as well as generation of heat. So
Very
both.
good.
So
So that is
so
a
that is
that is a problem in all the fuel cells. That is, it generate electricity, but byproducts. Sometime if you see PMFC, byproduct is water, and byproduct is heat. So
yes,
in
sir.
Japan, actually, they are able to do a lot of research in cogeneration. Other countries, they are only into research with electricity generation by fuel cell. But Japan, what they're saying is, with this electricity generation, it's a exothermic reaction. A lot of heat is actually produced. So the fuel cell can be very big. So big as a maybe it's around 10, 12 feet high length, and so it's bigger like a room certain times. So in that case, huge
Mm.
amount of heat is produced. If we can tap the
Yes,
heat
sir.
and if we can convert it into electricity or something, or that heat can directly be used to heat up water or for room heating and those kind of purposes. So a lot of research is taking place in Japan on this cogeneration. So this is a term actually which might not be known to other people. That's what I asked you to explain. So you know what is
Yes, sir.
cogeneration. Good. So go
Yes,
for
sir.
SOFC then. Go for
Yeah.
SOFC.
So SOFC, the name originated from the electrolyte which is used. It is solid ionic conductor, and there is a small advantage here of using a solid ionic conductor is that if you have a solution or a polymer, it will be prone to get corroded. But as we're using a solid ionic conductor here, it doesn't have that problem. And best example is yttria stabilized zirconia, which is one of the example as a electrolyte for SOFC. And the operating temperature here is about 1000 degrees Celsius, which makes it best application for stationary power generation, not for vehicular application. Next, talking about the electrical efficiency, it is about 50 to 60%, and cogeneration is also possible. And once we were talking about SOFC, we know that the temperature here it is about 1000 degrees Celsius, which is one of the highest among all the fuel cells which we have discussed till now. So there was a research done on how to like use a fuel cell of intermediate level, and that gave rise to something known as a intermediate temperature solid oxide fuel cell, which is abbreviated as ITSOFC. And this fuel cell is just a derivative from the SOFC, just that the temperature it's little reduced, that is to an intermediate level compared to the SOFC. So these are all the fuel cells types which we have discussed, and all of the parameters which we have discussed till now is summarized in this table. This table could also be found in the textbook. So all the parameters which we have discussed, like the fuel electrolyte, is already discussed in our previous slides. So if anyone has any queries about this table, we would be very happy to uh, like respond to those queries. So I'll just move to the next table, and
Correct.
here comes the energy versus relative cost. So for all the fuel cells, like all the fuels which can be used as a fuel for a fuel cell, is like we have hydrogen, LPG, gasoline, methanol, and ammonia. And these are the two parameters which we are judging them on. So this is the relative cost and megajoules. So we want the relative cost to be as less as possible and energy to be high as possible. So overall, this parameter should be the second parameter should be as low as possible. And the
Correct.
first parameter is the usable energy. That is, we need more energy. So the more is the value of the first parameter and the lesser is the value of the second parameter, the best is that fuel.
Correct.
So we can see that when hydrogen is used in a plant, it has 118.3 and relative cost is 1. And when it is used in cylinders, it has 120 megajoules per kg and 7.4. And this 7.
I have something to suggest here.
Yes, sir.
Whenever you are saying hydrogen, so this 95% pure in plant and 99% pure in cylinder. So they all
Yes,
are properties of hydrogen, right?
Yes, sir. Like in
Fine.
the gas.
So listen. It's correct. It is understood. So what you do is the first three rows in the first column you merge.
Okay.
Is it understandable? So
Yes, sir.
whenever you're submitting it, the first three columns, at least first two columns, you should merge. So hydrogen 95% pure at plant, that should give you usable energy of 118.3 and relative cost as 1 watt.
Okay, sir.
1 watt. What is the unit? Dollar, rupee.
Uh, so relative cost, they have not given the with respect to what currency they are measuring. I
So
may
you
not
make
be able
it
to
dollar
comment.
then. You make it dollar. So relative cost dollar per megajoule.
Okay, sir.
Understandable. So
Yes, sir.
first one is because hydrogen itself is one row and that actually doesn't look good. So in second line only you write 90 H2 instead of hydrogen you can write H2. So H2 95% pure. So first row, the whole first row in that case would be gone. Otherwise it looks something incomplete. समझ में आ रहा है?
Okay. Yes, sir.
So H2 95% pure at plant, that will be your first row, and H2 99% pure in cylinder, that should be your second row. So please do this change, update, and before submitting. Yes, go for the third row, LPG.
Yes, sir. So LPG, we can see that it has usable energy of 47.4, which is quite less as compared to 95% purity of hydrogen, which was being used in plant. And relative cost is about zero point 0.5, which is plus point as compared to the previous which you have discussed. Coming to gasoline, gasoline, it has a comparable usable energy compared with the LPG, and also a comparable relative cost as compared to the LPG. But we can see that in terms of usable energy, it has a less advantage, but in terms of relative cost, it has a higher advantage. So overall, we can say that one thing has a plus point in one parameter, and other thing has plus point in other parameter. So these two are like comparable, like LPG and gasoline. Coming to methanol, methanol doesn't even rank as compared to LPG and gasoline. It is having a usable energy of 21.8 and relative cost at 3.3. And ammonia, like as I mentioned earlier, like LPG and gasoline can be competent to each other. Similarly, methanol and ammonia, they are competent to each other. Like ammonia, it has lesser usable energy, but compared to methanol, it has a higher relative cost, like high relative cost and lesser megajoules. So this high relative cost and lesser megajoule, it makes it one of the drawback as compared to methanol, because I just mentioned that this value should be as low as possible. So ammonia compared to methanol, it lacks the usable energy as well as the relative cost. And talking about gasoline, it also has a lesser usable energy and it has a higher relative cost, which makes it one of the drawback as compared to LPG. Before I had mentioned that this parameter should be high, which is incorrect. So there is this formula should be taken into consideration, that we want the relative cost to be low and energy should be high. So since this value is high, it indicates that it is having more internal losses as compared to LPG. So overall, if we want to conclude, then LPG is better than gasoline, is better than methanol is better than ammonia. Next, coming to the hydrogen storage system. So in the hydrogen storage system, we have property of hydrogen, that atmospheric hydrogen has less energy density and not suitable for storage. So what are the storage methods for storing hydrogen? We have compressed and liquefied methods, and also using metal hydrous and non-carbon nanotubes. This compressed and liquefied method is little conventional, and metal hydrides or carbon nanotube, it is advanced method. So I just mentioned that compression method, it is costly. Why? Because once the textbook Iqbal, the author says that for compressing hydrogen, it requires several hundreds of atmosphere to compress hydrogen, and it also requires for like refrigeration of about cryogenic temperature. Cryogenic means very very low temperature. On the other hand, the method of storing, which involves the metal hydrous and carbon nanotubes, it requires just several tens of atmospheres for compression. And one more positive advantage is that it supplies, like it has a capability to absorb and release hydrogen as a function of pressure and amount of whatever it is stored in the plant. And one of the drawback of the advanced method, that is the metal hydride, is that it is heavy. The weight of the storage system would be heavy. So there are research going on to reduce the weight of this second advanced method. And one more plus point of the advanced method is that the amount of hydrogen atoms stored compared to that of compression is higher. Like you can say the density of
Correct.
hydrogen stored in metal hydrides or carbon nanotubes is higher as compared to the compressed one. And one more thing I want
Correct.
to
Next slide,
highlight.
please.
Yeah, and one more thing, sir, like the safety, like there is a discussion going on with respect to safety of the storage of the hydrogen gas. Like Ford, they had proposed a report saying that if there is a better safety mechanism implemented for hydrogen-based fuel cells, then it has a potential to overcome the safety which is already existing for gasoline-based vehicles, IC engines. So.
Correct.
And there are two companies which is working on this, that is Sandia National Laboratories, and one more is Air Products and Chemical Incorporation. So these two companies are working on this aspect.
Correct.
So coming to reformers, so the definition of reformers is that it's a fuel processor that breaks down a hydrocarbon into that is a hydrocarbon is like a best example is methanol into hydrogen and its other products. So what is the need of having a reformer? So these are the advantages. Like it is easy to handle. Like as compared to hydrogen, we know that it is very inflammable. So it is difficult to handle. So this reformer, like it is giving you easiness in handling the energy resource like methanol. So the reforming techniques are steam reforming, partial oxidation, and autothermal processing. There are two types of steam reformers in use. One is with respect to methanol, and one is with respect to natural gas. So gasoline-based reforming is costly because it is expensive and complex. And most promising reformer is methanol because of its easy reformability and it is liquid at room temperature. So this is about a short description of reformers, and we'll discuss on how reformer works, and we'll also compare it with hydrogen gas. So I have like 2 points. The red color indicates with respect to methanol, and the second blue color indicates with respect to natural gas. So with respect to methanol, it is carried out by supplying heat to the mixture of steam and fuel over catalyst, whereas in natural gas, the mixture is fed to a reformer containing a catalyst which is known as a nickel. So the steam to carbon
Okay.
molar ratio is 3.5:1 at 760 degrees Celsius. So that mixture is passed to a low temperature water gas shift reactor. I will tell you, like the reformer, I just mentioned that reformer is a fuel processor. So a fuel processor consists of a reformer as well as a water gas shift reactor. So we know that after having this mixture, we are passing it to a water gas shift reactor containing CuO and ZnO as catalyst at 230 degrees Celsius. Next, what happens is that there is a reduction in the CO level because CO, it has a property that it will poison the anode platinum catalyst. So by this water gas shift reactor, the CO level, it will be reduced below 0.5%. And the overall reaction is this is CH3OH H2O, that is methanol plus water gives you hydrogen plus carbon dioxide. And we know that major pollutant is CO2. And the reason why we prefer using reformers is that there is infrastructure which is already available and distribution is already in place. So that's why a thought came about using reformers. And comparing methanol with hydrogen is that methanol is violently toxic, whereas hydrogen is innoxious. Innoxious means it is not harmful. And like the methanol, it has a tendency to accumulate in enclosed spaces. Like if there is no proper ventilation, then it will be accumulating there. And if it gets accumulated beyond a certain threshold, it will be having a tendency to explode. Whereas hydrogen, it can easily exit, being in gaseous form. So next we come to the fuel cell used in EV. This is the block diagram. I'll just before coming to these points, I'll just explain this block diagram. So we have a fuel cell controller, we have a fuel cell processor. We just discussed about this fuel cell processor, which is containing steam reformer as well as a water gas shift reactor. And then we have a thermal management, and we have fuel cell stack. We have this like in EV, we know that a battery, like a selective batteries, they are arranged in series and parallel combination, and that we call it as a battery pack. Similarly, we have a fuel cell stack because there is a characteristic of a fuel cell that it is like a current source and it has a low voltage. So in order to get a desired voltage, we need to put it in stacks. So that's why we have a fuel cell stack, and then we have a DC to DC converter. This DC to DC converter, it will convert the required it will convert the voltage, input voltage, to required voltage, which is good for charging the battery, and it has also it will convert the required voltage to another voltage which is required for running the motor. So it will, in one way, it will act as a booster when it is running for the motor, act as a step down voltage where it will charge the battery according to the rated battery charging voltage. Next, we have a power inverter. Like if we are using an AC motor, then we obviously require a power inverter, and then we have our electric motor and the differential and these two wheels. So I'll come to this now, these points. So a fuel cell EV consists of a fuel storage system that is likely to include a fuel processor and a raw fuel hydrogen, and a fuel cell stack and its control unit, a power processing unit, and controller and propulsion unit. So I have discussed all this in my block diagram, so I won't waste much time in this point. Next,
Yes, Kaushik, this slide actually you have explained. All the other parts also you have explained. So you can go to next slide because all the sub parts you have explained. So I guess this is the last slide.
yes, sir. This is the last slide.
Yeah. So this is a characteristic of fuel cell. Just answer it in short and finish your presentation in 2 minutes.
Yes, sir. So characteristic curve is that we have a mode called as current limit mode when a vehicle, that is FCV, is using 100% utilization. When it comes to that point, there is a lot of internal losses, and that's why there is a need of controller which will ensure that the vehicle is operating outside the regime of the current limiting mode. And next, we have operation of fuel cell at reduced flow rate minimizes the wastage of fuel. This is just a characteristic that if you have the operation at lower rate, it will reduce the wastage of the fuel. And output power deliverability is directly proportional to the fuel rate. The more the fuel rate, the more the output power, as simple as that. So then we have an ideal controller. Like ideal controller, as explained by the author, that he says the fuel delivery rate should be exactly as same as the consumption rate by the cell. So that cell is termed as an ideal controller. And there is a need of a reserve energy battery to provide when there is an uninterrupted operation due to slow response characteristics of the fuel cell. So there is a need of a battery, and this is one of the drawback of a fuel cell. And the byproducts of a fuel cell are water, which is in the form of steam, and excess hydrogen. And this excess hydrogen is one of the most major drawback of fuel cell, that we are supplying hydrogen to produce electricity, and that is getting wasted. So this is one of the drawback of using a fuel cell. So there are research going on to make it more and more efficient. And coming to this graph, we can see that the potential is decreasing and decreasing and decreasing, and the current is increasing. So overall, we can see that the power produced by the fuel cell, I mean the stack power, it is going on increasing. So we can conclude that as the current is increasing, the voltage would be decreasing, but the power requirement would also be increasing. So it means that once if you come into the current limiting mode, then there will be a lots of internal losses. So because of the internal losses, there won't be efficient utilization of your vehicle. So that's why there is a need of controller. So that's what is shown in this graph. So if there are any queries, I'll be very happy to answer those.
Yeah. So just tell us about which of these fuel cells is most widely used for vehicular application.
So fuel cells, as mentioned by Bhavana, like she mentioned about alkaline-based fuel cell, and also one more fuel cell. I'll just come to that.
Proton exchange membrane fuel cell.
Yeah. So
So
proton
it is
exchange.
PMFC fuel cell, which is most widely used in case of vehicular application.
Yes, sir.
And what is the main drawback? Bhavna, if you please turn on your video, question answer session. So what is the main drawback of PMFC fuel cell?
So proton exchange membrane fuel cell.
Yes, what is the main drawback of PMFC fuel cell if you are going for using it for vehicular application? Where are we getting stuck? What is the main drawback?
Sir, it is not providing much efficiency as that of alkaline fuel cell, sir. Like if
Much. So I would like to tell you because by luck or whatever, so this PMFC fuel cell was my PhD topic. Main drawback is it is providing whatever efficiency is required, so that much is there. But the thing is very costly. The proton exchange membrane itself is very costly. That time we had purchased so 1 square meter of proton exchange membrane from DuPont we had purchased. I told you in the class also. So it costed around 36,000 rupees 1 square meter. So if it's a big fuel cell, in that case you need quite a wide or area of that membrane, and it's highly costly. So whenever you are using it for vehicle, maybe we have to change the membrane frequently. That is also another problem because that membrane actually is the, you can say, the filter, and it goes bad frequently. So little bit of reverse ripple and all this thing in the output side from the input side. So from the output towards input there comes some ripple, and reverse ripple actually damages the fuel cell and it punctures the fuel cell, that membrane. So proton exchange membrane is very sensitive. It is highly costly. So this is the main soft point in case of the fuel cell. Kaushik, are you there?
Yes, sir.
Okay. So a good presentation. I find in the last slide, so there is a formatting issue. That again I'm telling you, all students, the justification is not there. Bhavna, whatever she had this slide, you check the top paragraph right side. So there is justification issue. So you just correct all this justification, formatting issues, and all these things, and you upload the slide in Google Drive. So
Yes, sir.
thank you. You can stop sharing, and the next group can